Now we'll get started. What does this equation tell you? The Van Hoff equation, last time we had to rely on thermodynamics to derive this equation, but in short, this equation is real, okay? This basically tells you you can get equilibrium constant. This is equilibrium constant and its relations to temperature, okay? So it basically tells you what your equilibrium constant might be depending on the temperature. This term generally is not affected by temperature change. Okay, this is a very big assumption for such equation. Okay, when you see this means standard condition. Okay, this is like a golden standard; it doesn't change. All right, but of course, when you go into more advanced chemistry, such as physical chemistry, you're going to get a lot of different correction terms to describe this behavior. And why is this equation important? Because plotting equilibrium constant, which you can determine by spectroscopic techniques, because you have other analytical techniques to tell you how much product and how much reactant you have at equilibrium. Okay, this is the key, equilibrium. At equilibrium point, that means there's no more change in your system. Then you can plot this data using this equation and experimentally determine heat of reaction. Okay, so what is heat of reaction exactly? If we going back to the energy diagram, okay? So this is energy, okay? This is heat of reaction, okay? The energy level of your starting material and energy level of your product. So if you go back to the previous chapter, we talked about bond energy. When you do a reaction, you break some bond and you'll form some new bonds, and the net value is heat of reaction. So it could be endothermic, that means it requires heat, it absorbs heat from the surrounding, or it can be exothermic. Okay, so that means it's releasing heat. In this case, everybody agree this is an exothermic reaction, right? So in the case where it's an exothermic reaction, we recognize there's a negative sign here, all right? So if we have an exothermic reaction, your natural log K versus 1 over temperature, this term here, will give you a slope like this. And the slope of this will tell you your heat of reaction. So we can experimentally, assuming you have a perfect reaction system, doesn't leak heat, okay, you have a very thermal insulating system, you can experimentally determine this, okay? So this is an exothermic, okay? So in some cases, you'll get a curve like this. That's endothermic, okay? So when the heat of reaction is exothermic, means releasing heat, it's a negative value. And negative times negative, that's why you get a positive curve, okay? Positive slope. Make sense? This equation could be confused with Arrhenius equation. So the Arrhenius equation is really come from and this EA is activation energy. That is the energy barrier you have to go over to get to product, okay? So from here all the way to the top, this is the forward activation and energy, okay? And from this transition state, that's called the reverse. Okay, that means for your product to go back to your reactant, you have to go over this energy barrier. So of course, this is a much higher energy barrier, right? So that's why for a thermodynamically favored reaction, it will prefer to be on the product side because your energetic prevent it from going backward. And the equilibrium constant is just to describe the position or the relative quantity of your reagent and your product at a certain condition. Okay, this is related to the reaction itself. Okay, and then the difference between forward and the reverse, okay, backward, will give you heat of reaction. Okay, that makes sense? So we review what's activation energy. So when we're talking about the collision model, where molecule will collide, it has energy, because when you're at a certain temperature, you gain the thermal energy, which is the kinetic energy for the molecule. They just move around very fast. Okay, when they hit each other at the right position and at fast enough speed, reaction is going to happen if it's energetically favorable. It will make more sense when we start talking about thermodynamics, but for the collision model, you have to remember molecule have to be fast enough and it have to hit at the right orientation. So that means the molecule could run into each other many, many times before reaction actually happen. And then for the reaction to happen, you have got to be patient. You got to give it time, reach to completion, reach to equilibrium. Okay? So when we are talking about activation energy, it talks about how many times the molecule have to hit each other, run into each other, and what temperature they're going to gain enough probability to react. Okay, so that's why we have this equation to describe reaction rate. Okay, so that's a difference. This is constant, okay, unitless. This is reaction rate. It tells you how fast things are disappearing, how fast things are forming. Okay, so some of you asked us, okay, what is this A stand for? So in the book, it's a correction factor, okay? This is a very rough model to describe what's happening based on experimentally measured value, okay? We never talk about where this R come from, right? I think in high school, teacher just gave you this, okay, gas constant, okay? This is actually measurable. So for those of you who are physics major, one day you guys will learn about it. How did this guy figure it out? I mean, I don't remember who figured it out, but someone figured out what gas constant is, okay? It's just a number that can be determined experimentally, okay? Anyway, so this is just to correct for your K based on this very rough model. All right, so what is this factor, correction factor, Intel? This is called frequency factor. And it is actually a function, okay? Just like what you will see with a lot of mathematical manipulation. This is a description of how frequent, P stands for frequency, okay? And Z stands for orientation probability. So if you think about NO, and then we have O2, okay? For a reaction to happen, it has to hit the O2 at the right position where they can exchange electron, okay? Where they can start sharing electron to form new bonds, okay? But before anything actually form, that's called transition state. At the moment they impact each other, okay? When they can decide separate, and then nothing happened, or they can react and form the final product, okay? All right, so this is frequency, and this is probability. I'm not sure about this particular reaction, right? But I can guarantee one of them is going to be more reactive than the other, okay? So the O have to hit onto the right atom at the right position for reaction to happen. That makes sense? So if we rearrange the Arrhenius equation, because at different temperature, we can get different reaction rate, right? So if we rearrange the equation, I mean, you're not required to memorize this equation. This will be given on your test, okay? But you need to know how to use them. You need to be able to plug in the right number, okay? T1 and T2. And this is the tricky part. This is different than here. But if you look at it, it's not really that different because there's a negative sign up here. Why do we keep the negative sign out there? This had to do with when we derived the equation, okay? You can rearrange it and it's gonna look like that. And the only difference, this is different, two different things, reaction rate versus activation energy, and equilibrium constant versus heat of reaction, okay? That makes sense? Okay, so you have to recognize this is Arrhenius equation, okay? I like to remind myself with this little a, it's activation, but it's also Arrhenius. Okay, and Van Hoff is a different guy. They did the study in the same era back in the early 1900s. All right, so next we'll talk about reaction half-life. The definition is the time it requires for your reaction, your reactant concentration to reach half. Okay, the amount of it decreased by 50%. That makes sense? So that means at time half-life at this predetermined time, the amount of reagent decreased by half. So by this definition, you can simply plug it into whether it's zero order, first order, second order, or higher order reaction. You can figure it out what your half-life is, okay? So half-life in the nuclear chemistry, that's important, okay? But the half-life is also useful when you're not very good at math, okay? But everybody know how to do something divided by 2, right? Then you can figure it out. Let's say we start with a concentration of 1 molar. With the concept of half-life, it's easier to figure it out how long it's gonna take from 1 molar to 0.5 molar, and how long it's going to take from 1 molar directly to 0.25 molar, right? You can do this amount of time is constant, this amount of time is constant. Okay, this is 2 half-life to get to a quarter of starting concentration. And maybe you will see 1/8, okay? Then 1/16. But then there's no point to do it multiple times, all right? Okay, so by plugging it into a first order rate law, and then we plug it in this half here, okay? So you will get, and then we can substitute this T to be the half-life, okay? All right, so these two cancel out, and we rearrange. That makes sense? Okay, become natural log 2 over K, okay? So by plugging the K, sometimes this is given, you should be able to figure out the half-life. Then you should be able to solve a simple scenario like this. How long does it take for the reaction to reach to a certain state? So in my own research, we talk about half-life in terms of how fast a polymer chain are breaking. Okay, so we can monitor the molecular weight of polymer with an instrument called gel permeation chromatography. But anyway, with an instrument, it can tell you what's the molecular weight. So for my own research, I'm interested in how fast of my long chain polymer become exactly half if its original molecular weight. So you see, before we were talking about concentration, right? I can also look at it as molecular weight, okay? Because when we're dealing with a long chain of polymer, I have a certain technique where it preferentially breaks at the middle of the chain, all right? So over time, my molecular weight, this is molecular weight with time. I can get a plot like this, and I can figure it out where is my half-life is. So let's say this is half of my molecular weight. Then this is my half-life for this polymer scission process, which means polymer breaking. So similarly, you can think of it as concentration, right? From a plot, you should be able to find, let's say this is 2 and this is 1, all right? And relative to this 1, that's 0.5. That makes sense? Sorry. Okay? Everybody gets it? All right, so let's continue the discussion from our previous lecture. Now we're talking about acid and base, right? And then you probably recognize that why we're talking about equilibrium constant. You can also use equilibrium constant to describe the acid and base behavior. And going back to the Arrhenius equation, Arrhenius also come up with the Arrhenius definition of acid and base, right? So his hypothesis is that if it can release hydrogen, okay, release a proton, that means it is acid, and if it can release a hydroxide ion, it is a base, okay? And we talk about the limitation, right? It does not really describe why amine is a base, okay? Amine is a base is because it's able to react with water and generate hydroxide ion. So Arrhenius, like his key research is on the ion theory, on electrolytes, okay? Now we're getting into the Bronsted-Lowry definition of acid and base. It talks about the ability to donate and accept protons, okay, H+. All right, and when you lose H+, for example, in water, it's going to give you a base, okay? And in previous lecture, we talked about conjugate acid and conjugate base, okay? So acid form conjugate base, base form conjugate acid, okay? So that fit into the description or the definition for the Bronsted-Lowry acid and base. That makes sense? Okay? So at 25 degrees C, when we're talking about pH, we normally refer to room temperature, okay? This is a constant. However, when you change temperature, the equilibrium between distribution of these two will be different. So in Le Chatelier principle, it talks about the equilibrium, it's a constant, okay? But the position may shift when you disturb the system, okay? So when you add a strong acid to water, it completely dissociates. It changes the amount of acid, okay? And since it's a spontaneous process, we'll go into that later on. But anyway, when you put acid into an aqueous solution, it's going to give you more of this hydronium ion. It releases protons and it makes things more acidic, and then you can change the pH. And then last lecture, we also talk about pKa. When we talk about pKa, it's basically negative log of a number, your acid constant. When we are talking about dissociation, we have equilibrium constant K, right? So the larger the K, because it's product over reactant, the larger the K, that means you're generating more acid in this sense, right? For an acid, hydronium ion. So that means at the high K, at high equilibrium constant, you're going to get a low pKa. And the lower your pKa is, the more acidic this proton would be, okay? Or because the proton hydrogen, we use it interchangeably, okay? So when you get into organic chemistry, the pKa of different functional group, different H, will be very important. Only the stronger base can take a proton from a weaker base. Okay, so this go back to concept of conjugate acid, conjugate base, and whether you can tell the acidity in different solvents. Okay, so in water, last course we talked about HCl and HBr. In water, they completely dissociate. So that means 1 molar of HCl that you put in solution, it becomes 1 molar of hydronium and 1 molar of chloride ion, right? So you cannot really differentiate the acidity in water, okay? So that is related to the concept of leveling effect. If you can read the book this weekend, you can learn about it, okay? And that is also related to auto-ionization. It's just a property of water molecule, right? But however, in an acetic acid, in a weak acid, you will be able to tell the difference because acetic acid is not willing to give off its hydrogen completely. So if we think about the pKa of acetic acid, it's very different than these, okay? All right, so we can describe Kw with the amount amount of hydronium ion and hydroxide ion, okay? And then we talked about previously when you're writing reaction quotient or equilibrium constant, if it's a liquid or solid, it's not something we concern because these things don't change, okay? So essentially Kw is a product of these two terms timed together, okay? So when we do a negative log of Kw, that allows us to, this is simple math, okay? By knowing the Kw and knowing the amount of H in the system, you should be able to get how much hydroxide you have in the system. So for pH, for the measurement of pH, we can either use pH meter, which rely on electrochemistry, or we can use acid-base indicator, right? So these indicators are some organic compound. Usually these are some organic compound. They're able to accept a proton or release a proton in such process. And the change in structure will result in a color change because it changed its physical property due to the structural change. Okay, so we talk about a more acidic compound. It's gonna have a very low pKa. We can calculate Kb using the equation where we focus on the amount of hydroxide that is being formed in the reaction. So these concepts are interchangeable, but let's go back to the discussion of relative acidity, okay? You probably do recognize this ion is come from sulfuric acid, right? It's a very strong acid and it have 2 protons to be given away, okay? So usually in solution, if you dissolve it, it's gonna give you 2 hydronium ion, right? Because the first one, the dissociative constant to lose 1 hydrogen, equilibrium constant is so large, you can't really get a value for pKa, okay? But for the second, it's actually measurable. You can get the pKa of 1.99. And the smaller this value, that means it's more easier for this compound to lose a proton, okay? Then we're talking about acetic acid. It's a weak acid, okay? It has a pKa of about 4.75. But when we get to phenol, it's soluble in water, but when it's present in water, it's solved by water molecules through hydrogen bonding. You have much less of this phenol would dissociate into phenolate and the corresponding hydronium. It's gonna stay in this side, okay? Relatively, you're gonna have more, if you dissolve these two in solution, in water, you will get more of acetate than more of phenolate, okay? Then finally, let's look at propane. Propane is a gas that we use to burn, okay? You need a very strong base to be able to deprotonate this. So usually, well, first of all, it's not soluble in water, so you cannot really measure it, but there are ways you can do it in organic solvents. You need a much stronger base, so that means when I mix a phenolate, okay, I can make a sodium salt out of it. In case of sodium salt, I can react phenol with sodium hydroxide. So when you form the sodium phenolate, since your hydroxide already consumed that extra proton and turn it into water, when I put this into water, let's assume it get a complete dissociation, right? If it see another acetic acid, it's gonna immediately pick up this proton. That makes sense? Because if you look at the scale, okay? And there's another example in your book, talk about this. Page 806, it compared the strength of different ions, okay? So generally, when a strong acid dissociates, its conjugate base is basically useless. It's happy to be dissociated completely. It doesn't want to pick up another proton. Okay, so usually it's the conjugate base of a weak acid. It has the ability to undergoing this proton exchange process. I want to look at figure 18.7, which is a page before. So it has a nicer figure to describe the proton transfer process for the Bronsted lauric acid and base. Okay, so we remember water, if you remember how to draw the Lewis structure, okay, now you see why Lewis structure is important, right? Now we know where the lone pair is, right? We know the water is a bent structure, and when you dissolve HCl, it's going to immediately pick up that extra proton, okay, and form a hydronium ion. And similar for base, you see that? The amine has a lone pair, and it has affinity to pick up another proton from water and generating ammonium and hydroxide, okay? So ammonium, you can also use it as an acid. If there's something stronger, something more basic, it's going to pick up that hydrogen, okay? Something more basic than ammonia, okay? It's going to pick up that hydrogen from ammonium ion. That makes sense? So the strength is all relative. You can go back to the table, and that will have a better trend out there. So I think you guys read about chapter 14, right? And it had description to talk about the relative strength of acid that is made of different atoms. So we said the more oxygen you have, the more acidic it could be. Okay, now I want to point your attention to these four. Which one is the strongest acid? So actually, when we talk about these, we care about the electronegativity of this. So whenever you see the fluorine ion, usually it has a very different property because the fluorine is very electronegative, okay? So it changed the bonding character. So by definition, this should be the strongest because this is most electronegative, okay? But we have to look at the experiment. All right, I forgot to write down the number here, but if you compare these three together, this one, because the iodine is more electron withdrawing, right? So this is going to be the strongest acid, okay? So next we'll look at, before we go into buffer, right? So we're going to look at polyprotic acid. This is called a polyprotic acid, okay? It has two Ka value, Ka1 and Ka2. So that describes how easy it is to lose the first hydrogen and how easy it is to lose the second hydrogen. So how many of you wear contacts? If you wear contacts, you have to rinse them every day to remove the protein deposit, right? You have to clean it. And you use a saline solution to do that. So sometimes if you get sick and go to an emergency room, they sometimes will put you on the saline injection. So have you ever think about what's in that saline solution? So it's a salt solution that meets with your physiological condition, right? It's basically an electrolyte solution. So a very common saline solution is called phosphate buffer. So this is then for phosphate and buffer solution or saline. Okay, so saline just means it has about 0.9 weight percent of salt, NaCl in it for the electrolyte. Because the next chapter we'll talk about buffer, but we won't get into it, okay? Now we just want to look at the property of polyprotic acid of phosphate, okay? We know phosphate is this PO4 3-, okay? So its original form is H3PO4. If you look at your page 813, okay, so I'm not going to waste time to write down all of these equations. But you can look at the Ka1. Okay, I just want to point your attention. Remember the previous discussion, the larger K, what does it mean? It's going to be more on the right side, right? So you see they have a multiple order of magnitude difference, okay? As you go down, this is to show that it's harder to pull away another hydrogen from the phosphate, okay? The reason why it had to be explained from the energetic of such reaction, okay? But for now, these are experimentally measured value, okay? So that means it actually prefer to go through the Ka1 and Ka2, and that is the fundamental reason for its buffer property, okay? What I mean by buffer is prevent the rapid change of your pH value under a certain concentration. So as long as you don't put extremely large amount of acid or base into a system, the pH is going to remain the same. And the key players are the first two equilibrium. If it's too acidic, it's going to use the phosphate ion to pick up more proton from the system to form the HPO4, okay? So actually, a K3 for potassium phosphate, sometimes it can be used as a base in organic reactions, okay? You did not hear that wrong. It can be used in organic reactions. So because it prefers to pick up protons, right? Where if we want to go backward from phosphate ion, so it's actually a little bit more basic than this guy. Phosphate is more basic than H2PO4. That makes sense? Now there's more, I think it's a little bit memorization to see whether salt will be acidic or give you a basic solution. In section 18.7, there's some description of what's going on. Generally for the if you think of a very strong acid, the HCl, HBr, HI, right? Nitric acid, their corresponding ion, because it's so favored to be completely dissociate, right? So generally the corresponding of these counter ions don't have much power to interact with hydronium ion. And if we look at the group 1A metal, okay, and as well as the second row, okay, the barium, strontium, calcium, they generally do not influence, their corresponding salt generally do not influence solution pH. But however, going back to the discussion on ammonium chloride, when you dissolve into water, it's going to be weakly acidic because the water is going to pick up a proton from this guy, okay? I think I didn't really touch on too much on Kb, but we previously talked about Kw is a product of Ka and Kb, okay? So you can do the simple mathematical manipulation to get what Kb is, okay? So when we're talking about whether it's an acid or a base, we basically look at when it's associate. When I calculate these constants, if Ka is larger than Kb, that means it's an acidic compound. And the definition for Kb can be found in the book. I won't go into detail, but the Kb is look at how much hydroxide ion that you're generating in your system. So finally, we will briefly discuss Lewis acid and base. Okay, so different from Arrhenius and Bronsted-Lowry. Lewis acid, Lewis base, that concept is referring to its ability to donating electron pair or accepting electron pair. So for the one that can accept electron pair, that's acid. For the one that can donate, that is base. So if you think about how the bonding is formed, you can see when you form the hydronium, it's water donating that extra lone pair electron to the H+, okay, because it's missing electrons. That's why it's H+. Remember the electron configuration? Now do you see the connection why we need to talk about bonding and electron configuration in the first semester? Now these things are coming back together. So a perfect example of Lewis acid and base would be boron. Boron, as you can see, it's in the middle of your periodic table, okay, it's so eager to get some electrons so it can get to the noble gas configuration that's the most stable, or it can lose some electron, okay? So generally boron is considered to be electron deficient because it wants the way electronegativity it is, and its difference compared to the surrounding atom make it more likely to give away electrons, okay? So a perfect example of Lewis acid and Lewis base, you can look at your page 828. BF4, this thing is generally, when you have a amine, it's gonna form this bond, okay? So this is a very classic example. If you buy BF3 from a vendor, okay, a lot of time it will sell you BF3 in ether. And the most common ether is diethyl ether. Again, the lone pair of it is gonna bind to the boron. It's gonna, or the boron, okay? So this is a classic example, and then we call this a Lewis acid because it accepts electron from other electron rich, okay? Other electron rich generally is nitrogen and oxygen, okay? They like to donate that electron away. So other examples, so how can we tell whether it is a Lewis acid and Lewis base? You can simply look at the electron flow. Does it have an extra lone pair? Okay, so another example would be SO2, and then we'll get into it in a little bit. So we know when we dissolve SO2 into water, it will generate this. So if you look at how the reaction happened, the lone pair of your oxygen atom, these electrons attack this electron deficient sulfur. Why is it electron deficient? Because if we look at the electronegativity, each atom, right? Oxygen is more electronegative, right? So the electron, even their bonding of form, most of the electrons are on the oxygen. Okay, so make this spot more electron deficient. So when the water molecule comes in, when it collides with the oxygen, nothing will happen. But since this is deficient, this can donate electron to here, and then you get into this intermediate state. But of course, what's special about sulfur is it could have d orbital. We talk about 1, 2, 3, but this is 3, 3, 3d. They have d orbitals that allows more electrons to come in. So in the end, you end up with something like this. Why do I bring up this SO2? Everybody likes to ride a car, right? So in your fossil fuel, a lot of time, where does fossil fuel come from? And animal and plants, right? And we know there are amino acids that have sulfur in it, okay? So naturally, these fossil fuel, when we just dig them out from the oil well, there are some sulfur in it. Industrially, there's such process called desulfurization, okay? Because the Environmental Protection Agency, there are laws require the industry to reduce the sulfur emission. There are processes that you can do to remove sulfur, okay? Then you will generally produce a lot of sulfur and separate it from your fossil fuel. But that residual amount that is present in your fossil fuel when you burn it, okay, when you try to get the chemical energy out of these alkanes, you're gonna, in the combustion process, you're gonna turn some of these organosulfur or inorganic sulfur into SO2, okay? So why is SO2 bad? When SO2 dissolves in water, it generates this. Okay, compared to sulfuric acid, it's not such a strong acid, okay? However, this can be further oxidized. So industrially, people actually burn sulfur on purpose to generate SO2, and then bubble it through water, okay? So you generate this, and then with the catalyst, we will do an oxidation process to convert it into sulfuric acid, okay? So in organic, you will see more of the use of sulfuric acid and how it can be used as an oxidant, but I won't go that far. So Once it's oxidized by ozone, okay, or it oxidized by hydrogen peroxide, you're generating sulfuric acid. And what did that do? When it rains, it provides acid rain. That it could be corrosive depending on the pH. So then what about nitric acid? Where could that come from? So we know in the fossil fuel, there could be nitrogen present, right? So in your car, there are something called a catalytic converter located near the exhaust of your car. So it basically is a heterogeneous catalysis system. Okay, it basically when you combust nitrogen, it will generate what we call the N oxides. It can, so we have a number of practice. It can be 2, right? It can be 1, and it can be N2O5, right? There are all kind of nitrogen oxide species. So in that catalytic converter, what happened is it's able to strip that hydrogen. Why do we need catalysis? It lowers the activation energy to make these reactions more feasible. Then you convert it back into nitrogen and water. So I think now we have completed this chapter 18. Okay, so we'll continue the discussion of equilibrium constant. When we're looking at the solution of inorganic salt, okay, and some of the ionic compound may or may not be soluble in solution in aqueous environment. So the perfect example would be the silver nitrate experiment that you guys probably have seen before. Silver nitrate, when you expose it to chloride ion, you will get this black precipitate, which is the silver chloride. But when we look at the equilibrium, not everything will precipitate. Everything has a solubility. When we see a precipitate, for example, in the last reaction that we did, the iodine did not precipitate until you have a lot of it, okay? It has some solubility in aqueous solution. If we're looking at this lead fluoride, we know if it dissolves, it's gonna become a solvated ion. So that means there are a lot of water molecules surrounded by this ion. If we would write the reaction quotient for such a reaction, we already know this is solid, right? So we care about what? The mobile ion that is formed in such process. So we can write square. So this will be an expression for reaction quotient of some such system. Okay, so at its limit, okay, when we're adding a lot of the PbF2 and we form a saturated solution, that means this system is at the equilibrium. Okay, no more of these PbF2 will be soluble in such system. Then we can use we can use a QSP, but since at that equilibrium, most of the time you will see KSP. So Q, you can use that to describe any system, right? But if it's at equilibrium, we call that K. So when the Q is smaller than K, we know that this reaction hasn't reached equilibrium. It still needs to produce more product. So in this case, we look at how much of these compound would dissociate, okay? But of course, you can look at it backward. We put in these amount of ions and to see what happened. Would you get precipitate or would you get a solution? So of course, when we talk about KSP, it's much more complex. I know I've been skipping all the complex ion because I would like to talk about it all at once when we get into complex ions. So that means the ability of these metal ions is capable of forming these complex, okay? So these complex, for example, when it dissolves, it's not simply Pb2+, okay? It could be Pb2+ with 6 water molecule that had its extra lone pair donating these electrons to the Pb. That makes sense? So we talk about Lewis acid, Lewis base. That's exactly what could happen. It could be other species where you have a Pb 1 fluoride, okay? So that could be also a component in such system. When we talk about these situations, what is the relative concentration? If it's too small, okay? If it's negligible, we will not discuss it. All right, so generally, when we're looking at KSP, okay, look at how much ion you can form. Okay, so that means when something is very soluble, when an ionic compound is very soluble, it can generate a lot of ions. The KSP is going to be very high. And then, so if the KSP is low, that means it's poorly soluble. And by looking at the KSP or the QSP, okay, because this is solubility, oh sorry, I forgot to mention, SP stands for solubility parameter. Okay, so you can look at a system and decide whether it reached to completion or not. And we'll do a sample problem, 19.6. So let's take some time to read through the problem. So when you see molarity or when you see weight per volume is given, you should be able to immediately to think about the question in terms of molarity, okay? Chemists like to look at things in terms of mole per liter, okay? If it's not in solution, we don't care about it, okay? We write our expression like this. So in this case, it talks about lead sulfate. It's a very similar problem you can do. So first you can calculate the molar solubility because the solubility is given, okay? It's 4.25 times 10 to the 3 gram per 100 mil. We can convert that to liter and divide it by molecular weight of your lead sulfate, then you can get the molar solubility. And by simply plugging it into this equation here, because you're generating sulfate, you only generate one sulfate per lead sulfate, so you don't have to square it. Then you can set that to x, then you can simply figure out your KSP. Okay, so going back to the second part, you can generally solve for the equation, okay? Set this to x because you will generate one mole of this that perfectly dissolved will generate 3 mole, right? So that's why in the end it's a cubic term, and you can figure that out. Okay, so this is just a simple practice. When you see KSP on concept exam, now you know exactly what that is. And then now I want you guys to discuss with your partner and look at follow-up problems 19.6b to see if you are able to do such calculation. So first we will need to get the formula weight of silver phosphate, right? So you can look that up on your phone. And then you can figure out the molar concentration of such things. And then you can write out the expression, what would you expect when they completely dissociate. We would not consider such intermediate ion in this case. Then you set up your equation, then you should be able to get the answer pretty quickly. Okay, so how many of you get this far? This should be quite simple, all right? You figured out the molar mass of your compound. The amount that is dissolved is given, right? And then it tells you about the volume. Please convert it to mole per liter, okay? Unless later on you can deal with millimole per mil, but millimole per mil is still mole per liter. I want you guys to become comfortable when you're doing calculation like this. At the perfect condition, okay, we would know the silver ion that's generated. There will be 3 times of this, but this will be this value. So from here, you can calculate KSP. Okay, now there are 2 effects I want to mention. When I get a perfectly soluble system, right? Based on Le Chatelier principle, if we disturb a system, it will have to shift the position of equilibrium and go to its most energetically stable state. So if I adding additional silver ion, a soluble ion, it's likely change my Q, right? Then that's going to be different than this equilibrium position. So when you're adding more silver, it's likely going to generate some precipitate, so it achieves to a solution system that has a minimal energy. That makes sense? So that's called the common ion effect. You can see this in a lot of these ionic salt. But for example, if your counter ion is a very common, it comes from a very common strong acid. Okay, so generally when you adding the counter ion, it's not going to do anything, okay, because it doesn't really have an affinity for the other ions, okay. So when we talk about complexes, we'll go more in depth, okay. And second is pH, okay. We can generate pH, and then of course when you change pH for something that can form a hydroxide complex, then you're talking about totally different or a more complex system. So I just want you to remember how to do calculation like this, okay. This should be simple, and that's all we have for now.